Section 4.3, prove triangles by side, side, side. Our goal in this section is to use side lengths to prove triangles are congruent. So in section 4.2, we talked about congruent figures, and in order to prove two triangles were congruent, you had to prove all three pairs of sides and all three pairs of angles. Realistically, it's not feasible to prove all of that every single time. So what we do is we have some shortcuts. So there are 5 shortcuts in total. Shortcut number 1 is side, 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 which you can abbreviate with SSS. So the side, side, side congruence postulate. This shortcut says if all three pairs of sides are congruent, then the triangles are congruent. So in order to use this shortcut, you have to prove all three pairs of sides. Some properties that come up a lot are the reflexive property. If you have a shared side, that one comes up a lot. The definition of a midpoint comes up. So if you know a point is a midpoint, you can say the two segments are congruent by the definition of midpoint. Those are also some things that you may see again in this section. Another definition we have in this section is the definition of stable. A figure is said to be stable if it exists only of triangles. So when you look at figures and construction and engineering and stuff like that, you'll see a lot of these braces to create triangles. When you look at old steel bridges, they have a lot of crisscrosses in them. Well, that creates a lot of triangles. That creates stability. So we look at these first two figures and we talk, is each figure stable? It's a simple yes or no question. This first one is not stable because we have 4 sides here with no triangles, so thus it's not stable. This other one on the right here is stable because if I look, every figure, if I were to trace them, is a triangle. So this one is in fact stable. Look at these last two figures, determine are they stable or not. So the one on the left is not stable because this area right here, if they had connected, then you'd have all triangles and it would be stable, but since there is not that piece, it is not stable. And finally, the one on the right here, I look, that's a triangle, that's a triangle, that's a triangle, that's a triangle. That is in fact stable. Just because it has a triangle doesn't mean it's stable. It has to consist of all triangles. Determine if ABC is congruent to triangle DEF. On one of these coordinate ones, what you are going to do is look at the triangle. So plot triangle ABC and plot triangle DEF. And then what's going to happen is you're going to notice you have some vertical, some horizontal things, and then compare the triangles. Right, next, so I've got the two triangles plotted. Next, I am going to count the sides. I have some verticals and horizontals, so I go 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And now I'm going to do the same thing with the sides of triangle DEF. 1, 2, 3, 4, 5. 1, 2, 3, 4. 4 does not equal 5, so are they congruent? No. If you are asked to explain, you would say that EF not, so you put the congruent sign with a slash suit for not. So EF is not equal to BC. And that is why they are not congruent. If these both matched, you could do the distance formula for the hypotenuse or Pythagorean theorem. Either way, if the two legs of the right triangle were congruent, the two triangles would be congruent. All right, and in a section called Prove Triangles, we wouldn't get away without doing a single proof. So we have that PQ is congruent to RO, and QR is congruent to OP. And we can see that they are marked on the diagram. We are asked to prove that this triangle is congruent to this triangle. So we're trying to prove the top and bottom triangles congruent, the yellow and the orange ones. So we look at and say, okay, on this yellow triangle, the only piece I don't have is OQ, and the only piece I don't have on the orange one is QO. Well, what we're going to do then, it's the same piece, so we will say it's congruent to itself. And anytime we say something is congruent to itself, it's the reflexive property. And then we will mark those. You notice we have a double hash and a triple hash already, so we just need to use the single hash. And now we have proven all three sides of a triangle are congruent. So what we will do is, since we have all three sides, we can say that the triangles are congruent. You can write SSS for side, 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 or you can write side, dash, side, dash, side. One thing that was suggested when I went to a conference is that when writing these triangle proofs, if you leave yourself a little margin here and then write what you have. So in the given, we are given two sides of our triangle. So we're going to write an S and an S for a side. And in statement 2, we have another side. And if I look here, I have all three sides in my proof. That's a way to check that if I'm using side, 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 I have all three sides. Or if I'm using one of these in the next couple of sections with angles and whatnot, I make sure that I've in my proof have them. I cannot imply anything. In a proof, I need to directly state somewhere in there where all three pairs of sides. So if I go through and count up, 1 pair of sides, 2 pairs of sides, 3 pairs of sides. All three pairs need to be in the proof.